Welcome back to our discussion of gravitation. We had introduced Unit 8, gravitation, at the end of last lecture, and now we are going to continue with that discussion. So I introduced to you the universal law of gravitation, in which essentially the amount of force experienced by any massive particle due to the presence of another particle is given by this formula here. And one of the important things that we demonstrated last time was that the force of gravity will drop off like the distance squared. So if you double the distance, you make the force of gravity 1/4 what it was before. If you triple the distance between the objects, you make the force of gravity between them 1/9 of what it was before, and so on. Now, I want to apply this equation to an example. Let's suppose that we have a satellite, which is in a perfectly circular orbit around the Earth, and we want to know what the speed of the satellite is. We're going to use the universal law of gravity combined with Newton's second law in order to deduce this. So, the universal law of gravity tells us that we would have a strength of gravity, force of gravity, equal to g times mass of the Earth, mass of the satellite, divided by the r squared, where remember that this acts from the center of one object to the center of another. So we've got the whole entire radius of the Earth plus however far the object is located above that. That is what we mean by r, this whole distance. And that is squared in the denominator. There shouldn't be any friction or other forces on the satellite, so that's the only force that goes into our sum when we apply Newton's second law. And since it's in a circular orbit, we can set ma equal to m times centripetal acceleration. Then we come up with this equation that you see here. The mass of the satellite cancels out, meaning that this speed is independent of the mass of the satellite. However, it does depend on what our altitude is, right? How high above the Earth we are, because this r here depends not only on the radius of the Earth, but how high I am above it. It's that whole entire r. So the higher you are up in orbit, then this becomes larger in the denominator, and that results in a smaller velocity required. The lower Earth orbit you are trying to execute, the faster the satellite will need to go. Okay, and let's take another example. We had started to discuss this last time about how we can arrive at little g based upon applying the universal law of gravity and also what we know about Newton's second law. Last time I had written this as a little g, the acceleration due to gravity, but we can equally well just go ahead and call that g. And so on Earth, if we plug in the Earth's mass and radius here in this expression that we talked about last time, we get that 9.8 meters per second squared that we had talked about. So I mentioned last time also that if I plug in some other mass or star's planet's mass or star's mass into this equation, and along with that planet or star's radius, then I can arrive at a different acceleration due to gravity on some other world. So let's take an example of what that means. Let's take a super Earth, for example, which has twice the mass of the Earth. And we want to know how your weight compares on this planet X compared to the Earth. And so that's basically like asking, what is the gravitational acceleration rate, right? Because your weight is going to equal mg on this planet. Okay, so your mass is not going to change, but g is. So how is this going to compare? Well, remember that g on the planet is going to be equal to capital G times mass of the planet divided by the radius of the planet squared. That's what we had on the previous slide. So we can write these things in terms of what we know compared to the Earth. Capital G is a constant that does not change. The mass now is 2 times the mass of the Earth, and the radius is twice the radius of the Earth. But when I square this, this becomes a 4 in the denominator and a 2 in the numerator, which then simplifies to being 1/2 of the gravitational acceleration rate on Earth. So that's what we have here on this planet. That means that my weight is only going to be 1/2 of what it would be on the Earth. Okay, so we've looked at universal law of gravity. In the previous unit, we looked at static equilibrium. Why don't we go ahead and synthesize and combine these two concepts into a problem-solving effort involving an astronaut on Mars? So this astronaut is standing on a beam that is sticking out of a building, and it's being held in place by the tension on this rope that you see here. And we want to know how far this astronaut can walk out onto the beam without disrupting this equilibrium. So we want to ask ourselves how many forces are involved here. Well, we've got some forces from the building pressing onto the beam. We've also got a weight force, we've got a normal force, we've got a tension force. When we think about all of the forces involved here, we're going to conclude that there are actually more than 4 forces. So let's take a look at the extended free body diagram to see what those forces are. So what are the forces due to the building? Well, we have an angle bracket here, right? That's what it says in the problem statement. It's connected to the building through this angle bracket, and so we've got a force pushing up on the beam and pushing to the right. That's why you see these two forces here. Then we've got the weight of the beam, which, as we said, in any extended free body diagram, we're going to depict that weight at the center of mass of the object as a regularly shaped object. That's going to be at the middle. If it's just the beam that I'm thinking about, I'm not yet thinking about the weight of the astronaut. The weight of the beam is going to act right down at the middle. Okay? Now, speaking of the astronaut, it's the normal force that is pressing onto the beam, right? So the normal force due to the person standing there, if I were to draw the person's free body diagram, then I would conclude that the normal force from the beam onto the person should be equal to their weight on this planet. And so this normal force, which we can call NBA by Newton's third law, should equal NAB, okay, but we don't want to right off the bat call that mg, even though it equals, this is going to equal the mass of the astronaut times g on this planet. Okay, and that's just by virtue of the fact that these two are in equilibrium here, and then Newton's third law demands that these two normal forces be the same. So therefore, this is the same as this is the same as this. And finally, we've got the tension of the rope, and remember that this is at a 30-degree angle according to the problem statement. Okay, so that's our entire extended free body diagram. And remember that when we are in static equilibrium and we want to add up the torques, we want to choose a reference point that will allow us to simplify our calculations if possible. So out of these possible reference points to put our rotational axis at, which should we use? Well, the answer to that should clearly be A, since with A, neither of these normal forces will have a non-zero lever arm, so they will not contribute to the torques whenever I sum up the torques for this static equilibrium problem. So let's go ahead and solve this problem. First of all, I need to make sure that I know what G is on Mars in order to plug it into this mg anytime I have a mass and I'm looking at the weight. So the G value for Mars is going to be equal to G mass of Mars over R Mars squared. And when I take the values of that, you can look them up online if you want. And when I plug them into this equation, I'm going to get a value of 3.7 approximately meters per second squared. So about a third of what it would be here on Earth, a little more than a third. Okay, so if I sum up the torques then that are at work here, I will have no contribution from either of these normal forces, but I will have a contribution due to the weight force that's right here. Okay, so that contribution will be in the negative direction, since it would produce clockwise rotation if it were acting alone. So negative mass of the beam times G on Mars, and then times the lever arm. If I call this whole lever arm L, then I can see that the weight is acting halfway down, so this is going to be L over 2. Now we also need to multiply by sine of the angle between these two things, but as you can see here, this is going to form a right angle, and sine of 90 degrees is just 1, so this is all I need for the torque due to the weight. But to that, I've got to add 2 more torques. So what about this normal force here? We've already concluded that it was equal to the weight of the astronaut. And so the torque then that's going to contribute will also be negative. So I still need a minus sign here. And we need m of the astronaut times g on this planet. And then what is my lever arm? Well, it's the distance that I'm looking for. I don't know yet what that is. That's what I'm trying to solve for. Okay, again, these are perpendicular. Sine of theta is just 90 degrees, so sine of theta is just 1. And so that is multiplied by 1. We don't need to put a sine theta in there. Finally, we've got the torque due to the tension. So the tension force is the force times the lever arm, which is going to be the entire length of this beam, right? This whole length, L, times sine of the angle between, and now this is that 30 degrees that I had here earlier. Okay, so if it's in static equilibrium, all of these things have to equal 0. Now, the other thing is that the forces would need to add up to 0 as well. But if I look at this equation, I can see that I actually only have one unknown here, so I don't even need to do an analysis and sum up the forces and set them equal to 0. I don't need a second equation. I have one equation and one unknown, so I'm good to go. The tension was given to me here as a maximum value. This is the maximum it can hold without snapping. So this is the maximum distance that the person can go. Okay, so I've got this. The length of the beam is also given to me right here. Okay, the mass of the astronaut is given to me, as is the mass of the beam. And so I can go ahead and plug everything in. And what I will find when I simplify this expression is that the distance should be equal to the following. Okay, It's not the prettiest expression, but that's what we get when we simplify. And plugging in this 30 degrees in for theta here, when we plug in all of those numbers, we will find the distance to be equal to 7.6 meters. Okay, so that's out of 12 meters. It's sensible. We can check our solution, make sure that that makes sense. I haven't gone like 20 meters out here. That wouldn't make sense since the beam is only 12 meters long. But it does make sense that it would be, more than 2/3 of the way out, perhaps. Okay, so that gives us a good picture of the forces involved due to gravity, but another thing we can talk about is what's going on with the energy. Remember that gravity is a conservative force, and anytime there's a conservative force, then the work done by that conservative force is going to equal the negative change of potential energy of that force. So I'm going to go ahead and derive what this expression is going to be, gravitational potential energy. Of course, we had the expression on Earth where we had U equal to mgh, but that's only good near the surface of the Earth. What if we want to apply something further out in space or universally? I'm going to go ahead and derive that expression. Don't be alarmed if you have not gotten to integral calculus yet and are not quite able to follow this derivation. The result is what you need. But for those of you who want to see where it came from, it's useful and instructive to do that. So what I'm going to do is plug in the universal law of gravity for the force here into this equation. So we have that G m over r squared dr, if we integrate, should be equal to the negative change of potential energy, which is to say the final energy, the initial energy minus the final energy. If I take the initial position to be out at infinity, that's where I'm going to set my zero value at. So u 0 minus u final. Okay, so, and all that has another minus sign in front too, sorry. So then this whole thing becomes just u final. Okay, and so then whenever I perform this integral, a lot of things can be pulled out of the integral, the g, the m, the other m, and it's just an integral of dr over r squared. Okay, and when I do that, I get that the universal way of expressing this gravitational potential energy is with a negative g m m over r. So it's very similar to the force law. We're just having a minus sign here and 1 power of r in the denominator. Okay, but the beauty of this expression is that I can use it anywhere, not just near the surface of the Earth, to understand what's going on with gravitational potential energy at other places out in space or elsewhere in the universe. Okay, and so when I keep this form of gravitational potential energy and plug it into my general expression for total mechanical energy, for example, if I was looking at energy conservation problems, then it looks like this. We've got the kinetic energy plus the potential energy in this form. So let's take an example where we're looking at a circular orbit of a planet around the sun, and we're interested to know something about the energy of this orbit. So going back to what we did before, where we're using the force picture, we were able to simplify a similar expression earlier, okay? And we could cross these things out and talk about the velocity, but let's just not do that for a minute. Let's only cross out the r's for now, and let's say what happens when I divide both sides of the equation by 2, because this mv squared looks very similar to kinetic energy. If I divide by 2, I have the kinetic energy. So dividing both sides of the expression by 2, I get 1/2 mv squared on the left-hand side and 1/2 gmm over r, which means basically that the kinetic energy is equal to 1/2 of the potential energy. This is also a result that you can find using, or that you can think of as, you may have heard, called the virial theorem. So if I look at the total mechanical energy for this orbit, it's going to equal the kinetic energy plus the potential energy. And I've just deduced that the kinetic energy is 1/2 of the potential energy. So that means that this is the total energy, mechanical energy, for a circular orbit. Now I won't go through the derivation for an elliptical orbit, but suffice to say that it is a similar process and that this is your result. Basically, we're replacing R with A, where A is the semi-major axis. We're going to learn a lot more about what that actually means, semi-major axis, when we start talking about Kepler's laws. For now, you can think about it as the average distance between the star and the planet, but there's a more rigorous definition that we will look at soon. Okay, finally, I want to end with an analysis of the escape speed here on Earth. In order for some object to go out into space and not really return, what we need is for the energy of the system, for the kinetic energy that you give it, to at least equal the potential energy of the Earth, right? So that is to say that if these two things are equal, then when I add them up, I get 0. If I solve for the velocity in that case, I get this expression. Notice that it is independent of the mass of the object, but it does depend on the mass of the Earth and the radius of the Earth. This equation has a similar form to the velocity of the circular orbit. Recall that for the circular orbit, we said that it was equal to g m of the Earth over r. And the difference here, though, is not only do we have the square root of 2, that's sort of an insignificant is of insignificant importance compared to the fact that this r means something different than this r. This is a fixed value. This is the radius of the Earth. That's however much potential energy you actually have. This depends upon exactly where you're located, how high above the Earth you're located, and what that total distance r is. Okay, so this is just a constant value. In other words, I can plug in the constant g, the mass of the Earth, and the radius of the Earth, and I can give you some number. That number happens to work out to be 11.2 kilometers per second. That's the minimum that you need in order to escape. Now, of course, rocket scientists also have to account for the fact that there's going to be certain drags working against the rockets that they design, and so they may have to try and overshoot this value in order to actually get off the planet. All right, so more about gravity next time.